Hello and welcome to this R tutorial. So now we know how to implement two feature extraction techniques. These are PCA and LDA, but these feature extraction techniques work on linear problems, that is when the data is linearly separable. And in this section we're going to see one new feature extraction technique, but this time adapted for nonlinear problems where the data is nonlinearly separable. So this technique is called Kernel PCA. Kernel PCA is a kernelized version of PCA where we map the data to a higher dimension using the kernel trick, and then from there we extract some new principal components, and we're going to see how it manages to deal with nonlinear problems. So we're not going to work on the same problem as we did in the previous sections with the wine dataset, but we're going to work on the same dataset as the one used in part 3 classification, because now we need visuals. We need to clearly see what happens. We need to see how Kernel PCA manages to extract some new independent variables, the principal components, even when the problem is nonlinear, that is, when the data is not linearly separable. And this dataset that we used in part 3, the social network ads dataset, well, remember it was clearly a nonlinear problem because nonlinear classifiers showed much better performance. So let's take this dataset and let's apply Kernel PCA to see how it will handle the nonlinearity. So let's find this dataset into our working directory folder. So we'll go to our machine learning A to Z folder, then part 9 dimensionality reduction. And here we are at the last section of this part 9, Kernel PCA. So that's the folder you want to set as a working directory. Make sure that you have the social network add CSV file. And if that's the case, you're ready to click on this more button here to set the folder as working directory. And now what we're going to do is take this logistic regression model, because you know, this logistic regression model is a linear classifier. Therefore, it will not be appropriate for our problem because our data is not linearly separable. So what we're going to do is take this linear classifier here, but we are going to apply Kernel PCA inside of it to see how Kernel PCA will save the situation. And so you will see that even if we apply a linear model, well, thanks to Kernel PCA that will manage to extract new principal components adapted for this non-linearly separable data, well, you will see that we'll get amazing results. So right now, let's copy the whole model here from the top down to the bottom, copy, and let's paste it in our Kernel PCA file. All right, and now, basically, the only thing that we have to do is to apply Kernel PCA at the right place. But before we do that, I would just like us to visualize again why this linear model is not appropriate for this dataset. So what we're going to do is take everything from here, because you know this will visualize the training set results by plotting the prediction regions and the prediction boundary. So we're going to take everything from here up to the top to import the dataset, apply the preprocessing phase, fit the logistic regression to the training set, and eventually plot the training set results. So let's do it. Let's visualize this again very quickly, and that will give us motivation to apply Kernel PCA. And here we go, all executed properly. So as a reminder, the points are the real observations, that is, our real customers in the social network, represented by their age and their estimated salary. So that's our real observation points. And our predictions are represented by these regions, the red region here and the green region here. And basically this red region is where our model predicts that the customer will not click on the ad. And this green region here is the region where our model predicts that the customers will click on the ad and buy the SUV. And so remember, the problem was that this straight line here is actually the prediction boundary generated by the logistic regression model. But since the logistic regression model is a linear classifier, then it has to be a straight line here separating the data. And therefore, remember, the problem is that it cannot make some kind of a curve here to catch these green users that should be in the green region. Right now they're in the red region. And so this clearly represents the fact that our data is not linearly separable, because we can clearly see that this prediction boundary here that plays the role of separator and that is supposed to separate the two classes, well, it cannot separate the two classes properly because, as you can see, these users are not in the right region. And so now what we're going to do is not make a nonlinear classifier like we did in part 3. You know, when we made kernel SVM, naive Bayes, decision trees, or random forests. Well, what we're going to do now instead is apply Kernel PCA so that we keep a straight line as the separator, as the prediction boundary of a linear classifier. That is still going to be the prediction boundary of a logistic regression model. But since we're going to apply Kernel PCA, Well, this will manage to apply some trick, where the trick is actually the kernel trick to map the data into a higher dimension and then apply PCA to extract new components that will be new dimensions that explain the most the variance. But thanks to this kernel trick, well, you'll see that we'll manage to get some new dimensions in which the data will be linearly separable, even by a linear classifier like logistic regression. So let's see that right now. I can't wait to show you this. I'm going to close this, and now let's apply kernel PCA at the right location. So you already know what this location is. It's actually not different than before. We need to apply kernel PCA right after the data preprocessing phase and just before fitting our classifier like logistic regression to our training set. So basically, we need to apply kernel PCA right here. So new section here, applying kernel PCA, and here we go. Let's do it. Alright, so first we need to install a new package that is called kernlab, which I don't think we've installed before, so let's do it right now. So we use the command install.packages, here we go, and in quotes, kernlab. Alright, so I think I already have it installed. Let's check it out. So here it is, kernlab, kernel-based machine learning lab. So I will not install it, but if you want to do it, you just select this line and execute. So I will just put this line as comment. Here we go. But then, since it is not imported, I will import it using the library command, kernlab. All right, and that will import it. All right, kernlab will import it. And now let's start applying kernel PCA. So as for PCA and LDA, we're going to start by creating an object, which will be the kernel PCA object that we will use to transform our original dataset into this new dataset after using the kernel trick. So we'll call this object kPCA, and then equals, and then that's where we use the function that will create this kernel PCA object. So this function is also kPCA, then parenthesis, and then let's input the different arguments. So let's check it out. Let's press F1 here to have a look at the arguments. So the first argument is x, and this is actually the data matrix or the formula describing the model. And here I'll give you a little trick. To describe the model very simply and very efficiently, we can simply input here a tilde and dot. And that will be enough for the kPCA function to understand what the formula is. Because then we will add the second argument, which is data, and that is actually the training set, but without the dependent variable. Because remember, kernel PCA is just a PCA technique where we use the kernel trick to map the data into a higher dimension and then apply PCA because indeed in this higher dimension the data is linearly separable, and therefore since we apply PCA in this higher dimension and PCA is an unsupervised technique, well, here for the data argument we just need to input the training set but without the dependent variable, and therefore as for PCA we input here data equals training set, then brackets to remove the dependent variable which is indexed by 3 because we only have 2 independent variables. Alright, and then the next argument is kernel. So kernel is the kernel you want to use to apply the kernel trick. Remember when we studied kernel SVM we saw that there were several kernels to use the kernel trick, and here we're going to use the most common one, which is the Gaussian kernel, and that is called here RBF dot. So that's our third argument, and so here we input kernel equals RBF dot. Alright, and then what is the next argument? The next argument is kpar. We will actually not use this one, but then we have a very important argument that is at the heart of dimensionality reduction, that is features, which is the number of features, the number of principal components you want to end up with. So here of course we would like to visualize the training set results and the test set results in 2 dimensions, and to have this in 2 dimensions we need to keep a number of 2 new extracted independent variables. So here the number of features will be 2 as for PCA. So we will input here features equals 2. Alright, and that's it for our kPCA object. It is ready to be created and to be used to transform our original dataset into this new dataset with the new extracted features derived from kernel PCA. So let's select this line and create the object. Here it is, kPCA well created, and now let's move on to the next step, which is to transform our original dataset into this new extracted dataset. So now things are going to look like what we did with PCA, but some things are going to change. So we will do it step by step and we will see where we need to make some changes. All right, so first, as for PCA, we're going to use the predict function to transform our original training set into this new extracted training set. So this new training set, with the new extracted features derived from kernel PCA, we call it training set underscore PCA. All right, and then equals, and then we use the predict function to do the transformation. And inside this predict function, we first input our kPCA object, as we did for PCA, and then the training set, the original training set. So let's do it, training set, the second one. All right. And as opposed to PCA and as with LDA, this will return a matrix and we need it as a data frame. So as for LDA, we will use the as.data.frame function. So parenthesis here and we close the parenthesis here to set this transform training set, the training set PCA, as a data frame. And as a reminder, we're doing this to give what the next function we'll use in the next sections expect. All right, so far so good. And so now let's select this line and execute this. And you're going to see what's going to happen and you're going to understand why we called this new training set PCA with a different name than the original training set. All right, so let's execute. Here we go. Execute it properly. And now let's have a look at our training set PCA that we just created. So I'm going to enlarge this so that we can see which one is training set PCA. That's the one. So let's have a look at this. I'm going to click on it. And here is our training set PCA. So as we can see, it is composed of only two columns, V1 and V2. So try to guess what these two columns are. I'm going to tell you right now, these two columns are the principal components that we obtained through kernel PCA. That is, these are our two new extracted features after all this mapping into this higher dimension, using the kernel trick and then applying PCA to the dataset mapped into this higher dimension. But now the problem is that in this training set PCA, we don't have the dependent variable, and we need it for the next sections because in our code template, we need to have the independent variables and the dependent variable. So what is the next step now? The next step is to add the dependent variable into this training set PCA. And so the thing to understand here is that we lost the dependent variable, but we kept the observations. That is, this one here corresponds to the first observation we had in the original training set, this one. So this first observation here has the 0 label, that is that this first customer didn't buy the SUV. This was the original independent variables. And then if we go to our training set PCA, well, this first customer is the same first customer as this training set. So it will have the 0 label in the purchase column. But then these are new extracted features, so of course we don't get the same values as for the independent variables of our original training set. So what we can do now is simply take the dependent variable column purchased of this original training set and add it to our training set PCA, because these observations here are the same observations of our original training set. And so what we need to do now is very simple. We just need to take our training set PCA, then we're going to add a new column that we'll call purchased. So by doing this, I'm just creating a new column that I also call purchased, because this new column is going to be the purchase dependent variable, and then equals. And then what I have to do now is to take the real purchase dependent variable column from the original training set. And we can do that because the training set PCA contains the same observations as the observations of the original training set. So here, to take the purchase column of the original training set, we just need to take our original training set, which is called training set, and then $, and then that's where we take the purchased column. So by doing this, I will add this new column purchased, and in this new column purchased, I will include the values of the purchase column of the original training set. So let's check it out. I'm going to select this line and execute. And now, as you can see, if I go back to training set PCA, this contains the purchase column of the original training set. So that's good. That's the next step done. And now we need to take care of the test set. And so to take care of the test set, we're going to do exactly the same as we did for this training set PCA. So let's copy this, copy, and let's paste it here. And of course, what we're going to do now is replace this training set PCA by test set PCA. And same here, we take the original test set to make the transformation. And then we're going to add the purchase column of the original test set to this new test set, that is the test set extracted from Kernel PCA. So test set here, and that should be okay. So I'm going to select these two lines here and execute. Perfect. Our new test set PCA is created. Let's have a quick check. So that's the test set, and that's our test set PCA with the two new extracted features and the purchase column. And now that means that we correctly applied Kernel PCA. So great, we are ready to move on to the next section. So let's go back to our Kernel PCA R file, and let's now fit the logistic regression to the training set. Now, do we need to change anything in this code section? Well, yes, of course we do, because be careful, we called our new extracted training set PCA. So here for the data argument, we need to specify training set PCA. So that's the only thing we need to change here. So we are ready to select this section and execute. All right, classifier ready. And now let's move on to the next section, predicting the test set results. And of course here, that's the same. We need to replace test set by test set PCA. Going to enlarge this a little bit, right? And that's it. We are ready to execute this section to predict the test set results. And here we go, we get our vector of predictions, ypred, for this new test set PCA. All right, now let's make the confusion matrix. We of course need to change test set by test set PCA. Here we go, and now it's ready. Now we can execute this line of code to get the confusion matrix. And here it is. We can have a quick look in the console by pressing CM enter, and we get 57 plus 26 equals 83. And since we have 100 observations in the test set, that gives us an 83% accuracy. So that's pretty good. And now let's get to the exciting part, visualizing the training set results. So very quickly, what do we need to change? Remember, we need to change the names of the independent variables and call names here. That's compulsory. So as a reminder, the names are v1 and v2. That's the name of the independent variables. So here we need to replace age by v1 and estimated salary by v2. And that's not compulsory. And anyway, we already have the good names, PC1 and PC2. So don't forget about that. And of course, we need to change the name of the training set because we called our training set PCA. So here I'm adding training set PCA, and that's perfect. That's ready to be executed to visualize the training set results. So we will only visualize the training set results, but let's make the same changes for the test set so that you can have a look at it yourself. So same, we're replacing age by v1, estimated salary by v2, and here we replace test set by test set underscore PCA. All right, and now let's have a look. I look forward to showing you what's going to happen. So I'm going to select everything from here up to the top here. That is the whole section to visualize the training set results. And let's press Command and Control plus Enter to execute. Here we go. The computations are being run. Alright, so these are the results of Kernel PCA combined to a logistic regression model that we apply on a nonlinear separable dataset. And so we can appreciate the contrast between the simplicity of the obtained results and the complexity of what happened behind the scenes. Because indeed we have this very simple results here with these two classes separated by this straight line, but what happened behind the scenes is that our original dataset in our original feature space was mapped to a higher dimension using the kernel trick to avoid too highly compute-intensive computations. And then by mapping our dataset in the original feature space to this higher dimension, well, first that created some new dimensions, and mostly that created a new feature space where our data was then linearly separable. But by doing that, we had more dimensions than the original number of dimensions, so we still needed to apply the PCA dimensionality reduction technique to end up with a lower number of dimensions. So then PCA was applied to this new feature space where the data was linearly separable, and through PCA some new extracted independent variables were created that are nothing else than the principal components of PCA. And eventually, we obtain this new feature space formed by these two new extracted principal components resulting from PCA, in which now our data is linearly separable and much better separated by a linear classifier. Alright, so that's it for kernel PCA, and that's also the end of this part, dimensionality reduction, and I'll see you in the next part, part 10, model selection and boosting, the last part of this course where we'll cover a very exciting algorithm in machine learning that is called XGBoost. So I look forward to seeing you in this next part, and until then, enjoy machine learning!